Let's take a look at logic gates. Logic is, of course, our signal state, on or off, true or false, 1 or 0. Logic gates really are amplifiers. And you remember that an amplifier was drawn schematically by a triangle. Now this logic gate is simplified. It only has one input and one output, and it simply amplifies the signal. Drawing the circuit, it might be a simple transistor circuit like this. However, notice that it is an inverting amplifier. If we get a high on the input, we get a low on the output. A low on the input makes a high on the output. So we draw this logic gate as an amplifier with this little circle on the output, which signifies it is an inverter, sometimes called a NOT gate. This is our first logic gate. It simply inverts the input logic. We'll actually wind up using this a lot, and sometimes you'll only see the circle, which is the same thing. It is an inverter. Now, if we had simply a non-inverting amplifier, we would draw a simplified version like this because we only have one input and one output. This is called a buffer. It separates the input signal from the receiving circuitry, but it can be used to clean up weak or noisy digital signals. If the input goes high, the output goes high. If the input goes low, the output goes low. Let's move up to another gate called the OR gate. Here's the schematic symbol for it and a simplified drawing. We have two inputs and one output. If both inputs are low, neither transistors are turned on, so the output also stays pulled to ground or low through the pull-down resistor. Now, I can't remember if I explained what a pull-down or pull-up resistor was, so I'll explain it right now. It's really simple. Let's say I have a push button, and I need a digital low coming out of it when someone presses the button. Now, I can't just have the wire going to the push button, because when the button is not being pressed, the wire is what we call floating. It's not connected to anything. And so digital circuits are very sensitive. That wire can pick up electrical noise galore. It could pick up electrical noise from the lights in the room, and your digital circuit would think you were giving 60 highs and 60 lows per second. We don't want floating wires. So we run a resistor in series with the push button going to positive. This is a pull-up resistor because it pulls the voltage on the wire up. When I press the button, it pulls the signal to ground or low. Now let's say I needed a high signal for my digital circuit when someone pushed a button. So we use a pull-down resistor, which pulls the wire low until someone presses the button, connecting the wire to positive or high. So that's what a pull-up or pull-down resistor is. We are using a pull-down resistor in our OR logic gate. If we put a high on the first input, it turns on this transistor, which pulls the output high. If we put a high on the second transistor, it pulls the output high. If both inputs are high, both transistors are turned on, pulling the output high. So logically, if we have a high on input 1 or a high on input 2, the output goes high. From this, we can build what we call a truth table, which simply shows what the output does depending on the inputs. If there is a high on any input, the output goes high. If both inputs are low, then the output goes low. Now, we can have an OR gate, which has multiple inputs. In all cases, a high on any input causes the output to go high. Next, we have the AND gate. Here's the schematic drawing of it, a simplified circuit. If both inputs are low, then neither of the transistors turn on. The output gets pulled low by the pull-down resistor. If we put a high on the first input, transistor 1 gets turned on, but it doesn't pull the output high because transistor 2 isn't turned on. If we put a high on the second input, transistor 2 gets turned on, but transistor 1 doesn't, thereby blocking the high signal from the output. The output stays low. However, if we put a high on input 1 and input 2, both transistors get turned on, pulling the output high. So our truth table looks like this. Now again, we can have an AND gate which has several inputs. All of the inputs have to go high before the output goes high. If we put the output through an inverter, we get a NAND gate, or a negated AND gate. The NAND gate is the exact same symbol, but you remember I mentioned that an inverter can be symbolized by just the circle? Well, there it is. So this AND gate acts exactly the same way any AND gate does, however the output is now inverted. So let's take a look at the original truth table of an AND gate, and now compare it to the truth table of a NAND gate. The output is the exact opposite of the AND gate. That's all. The same can be done with the OR gate. We throw an inverter onto the output. It becomes a NOR gate. Let's compare the truth tables of the OR and NOR gates. Now let's take a quick look at the circuit drawing of the AND gate. We're using bipolar transistors, which, if you recall, have a very specific forward bias voltage, 0.7 volts. Now, it's very low. In fact, it's so low that depending on the circuitry, you could get false highs just from electrical noise. Now, if you have another logic gate further upstream, operating at 20 volts, for example, its low signal might be like 1 volt. That's more than enough to turn on the transistors, so you get a false high reading. So we simply put a voltage divider circuit on the input of the transistor, and we design the circuit so the resistors divide the incoming voltage, so that right around the half of the operating voltage, the transistor gets a sufficient forward bias to turn on. Now the reason I say half the operating voltage is because there could be line loss from the upstream circuit, a voltage drop over the wires, for instance. So a high signal might be several volts lower than the operating voltage, but it is a high signal. So if we aim for the halfway mark, that should remove the majority of any false signals, but still allow for a weak high signal. But because the transistor turns on at a very specific forward bias voltage, we need to know what our operating voltage is before we even design the circuit. So a standard was set called TTL for transistor-transistor logic. TTL uses 5 volts as its base operating voltage, and the circuitry is designed around that standard. The supply voltage has to be within 0.25 volts of 5 volts, so between 4.75 and 5.25 volts. However, if we swapped out our bipolar transistors for MOSFETs, the circuit functions completely differently. If you'll recall, MOSFETs don't have a specific turn-on voltage. The resistance simply follows the input voltage. The higher the input voltage, the lower the resistance. Because of this, logic gate chips using MOSFET transistors can operate on a much wider supply voltage, with the logic levels of high and low simply being proportional to the supply voltage. Your highs need to be as close to the positive supply voltage as possible, and the lows as close to 0 as possible. In your kit, you have a 4011 quad NAND gate chip, which uses MOSFETs. So it is an operating voltage of 3 to 15 volts, far less stringent than the 5 volts plus or minus 0.25 volts required for TTL. Now there is one more gate to discuss. The exclusive OR gate is the OR symbol with an added line at the back. With exclusive OR gates, either input 1 pulls the output high or input 2 pulls the output high, but if both inputs are high, the output goes low. So it's exclusive. It's either one or the other exclusively. Here's the truth table for that gate. If we stick an inverter on the output, boom, we have an exclusive NOR gate and its corresponding truth table. So in your kit, you'll have that 4011 chip, which is a quad NAND gate. It's a chip with 4 NAND gates built into it. Here's the internal schematic, and that pinout is in the downloads section, as well as a couple of experimental circuits. Use a couple of your momentary push buttons you received in your kit, and remembering the NAND truth table. Simply wire the push buttons with pull-down resistors to the inputs of one of your gates, slap an LED and a resistor on the output. So remembering, an AND gate will always output a low unless both inputs are high. The NAND gate is a negated AND gate. So the output will be the exact opposite. The output will always be high, except when both inputs are high. Interestingly, you can turn a NAND gate into an inverter by simply tying the two inputs together. So in this circuit, you have simply converted the NAND gate into an AND gate by running the output through an inverter. So it was inverted twice. So go ahead and build those circuits and play with them a bit. In the next lesson, we'll use this chip to make a special function circuit.